So my goal for today is to do kind of a lab report boot camp. Um, this happens every year. I get a first set of lab reports in, and it's usually not what I want. Um, Sometimes there's just stuff people could do better. Sometimes people don't pay attention to all aspects of the lab report style guide. And sometimes it's just awkward because the lab report style guide is written to, you know, with a kind of a generic lab in mind, but sometimes it's not clear how to apply certain things you're supposed to do in general to the specific lab that you're doing this week, particularly in something like your first lab this semester, where the result was kind of a qualitative thing rather than a quantitative thing. It's hard to know how to deal with some of that stuff. And so what I thought that I would do is to kind of take a moment to do a sort of like a boot camp about lab reports, uh, and hopefully try to help you guys refine some of those assignments that you've already turned in. At this point, I've got a slate of the first set of lab reports in, and I've looked at them. I haven't put grades on them yet because I want to give you guys a chance to maybe revise some stuff before I put a number down. The lab that was due this week, so far I've only got one submission, so I haven't seen any of those, so please get those in. But
so there is a chance you can change the due date for today?
I'm not going to change the due date because it was definitely due today. But you can always turn things in late, and like if you do a revision of something you've already turned in, I'll grade it according to the original turn-in date. So the idea is that, if you're turning in something for this week, make sure you turn in what you've got on time so that you'll get credit for being on time, even if you revise it later. Does that make sense?
Okay. Yeah.
So let's see if we can't make some sense out of like how to make a lab report. Hopefully by the end of the day, you guys will be writing lab reports like a boss. So the big thing in lab reports is, we have, in a technical writing sense, you have to fight against certain instincts that have been ingrained in you by your English professors since time immemorial. I remember when I first learned how to write essays back in, elementary school or whatever, and, they had a kind of, sort of, here, do an introduction, do a series of paragraphs, then write a conclusion. And they were very rote about how they wanted you to approach that, because they're trying to get you to build a sense of what a logical argument looks like and how to progress through a logical argument. And for elementary school kids, they usually have no idea how to express themselves. And I noticed that as I got older and I started writing papers, I started to feel a lot more confident as a writer. And I was willing to sort of break out of the very strict procedures that they taught me in elementary school, whereas a lot of my classmates kind of stuck to that, and it made their essays really kind of boring to read and mine a little bit better. When you read stuff that's written by professional writers, they don't have a formula, right? But they've also internalized some of those earlier lessons in such a way that they know when you can deviate from that in a way that will make your writing better rather than make it worse. So some of that is we have to learn how to be confident enough in writers that we can, go off the script in a way that makes sense, while not opening things up to complete anarchy and terrible writing. But in those rote procedures you guys learned back in elementary school, they were often very flowery. You often spent a lot of time doing, attention-grabbing quotes or, glittering generalities. And in a technical paper, you don't do any of that. In a technical paper, it's all business. You want to be straight to the point. Don't waste any time. Don't waste any words getting what you need to say said. So, when it comes to writing a technical paper, step one is don't bother with flowery stuff. It impresses your English professors, but your science professors are going to be like, whatever, what's the point? So that's going to be something you want to avoid. Some of you guys feel compelled to sort of pad out your word count with extra nonsense that doesn't really get to the point you're trying to make. Another big sort of no-no that I'd like you guys to make sure that you don't fall into this trap is I need you to make sure you identify the objectives. Right? I shouldn't have to guess reading your paper what it is that you're trying to do. In fact, in a scientific paper, typically the title itself tells you what you're trying to do. The first paper I ever wrote was called Measuring the Charge of a Vortex in a Type II Superconductor, Experimental Design and Data Analysis. That was the name of the paper. So what was I trying to do in that paper? I was measuring the charge of a vortex in a Type II superconductor, right? No, having read the title, you know what I was trying to accomplish, right? So the same thing should be true here. You want to make sure that it is absolutely clear what goal you're trying to accomplish and what that goal looks like. Now, I don't want to put anybody on blast here. So I'm going to do a screen share, but I'm going to try to crop out any identifying information. So if this is your paper, shh, don't say anything. I'm not trying to embarrass you. But what I am trying to do is to point out a very common mistake that a lot of students made. So let me see if I can do this. I am going to swap over to here. And who was I pulling up? All right. I'm going to pull up a background section from a student who shall remain nameless. And I'm only going to share a portion of the screen. All right, so right now you guys shouldn't see anything. Oh, you should see something, yeah. And so what I want you to focus in on is this background section of this student who hopefully you cannot see their identifying information. And if I'm looking at that background section, one of the issues is that they don't tell me what it is that they're trying to accomplish, right? They're saying for this 1D kinematics lab, they set out to accomplish approximately 5 objectives using the PhET simulation, the Movie Man simulation. And then it says, for the first 3 objectives, we're asked to generate a position graph similar to the one that is given. Now, imagine that you're a person who's been handed this paper, and that's all you've seen. You don't know what those graphs look like. You don't know what those graphs are supposed to look like. So later on in their results section, when they show you their graphs, you have no way of evaluating whether or not those graphs accomplish the objective or not, right? So you want to make sure that you spell out what the objectives were that you were trying to accomplish, because you're imagining that this paper is being read by someone who isn't me, right? Someone who wasn't there in the class, they didn't do this assignment, they didn't read the handout. Your document is the only thing that they have to judge what you've done by. And if you don't tell them what those are, you've done them a disservice. So make sure that you identify what the objectives are. So in the case of this particular lab, I would probably include maybe a screenshot or at least some figures showing what each of those graphs look like. Right? If you fail to do that, you won't be getting the full points for that background section. Does that make sense? So if I look at, here's another background section from a different person. And they did a better job of stuff. sort of. Although, if you read carefully, you're gonna notice something a little bit wacky. So here you can see from one of my students that, here they have, here's their background section. Here we're gonna replicate a series of graphs, yada, 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 and oh, here's some graphs. Now, does anybody see what's wrong with this picture?
They are in a different order.
No, it's not even that, actually. So
There's no equations in the background?
well, there's no equations. We'll deal with that in a minute. Right now, I'm just talking about the identifying of the objectives. So read that first paragraph and tell me what doesn't belong.
They don't have a name. The
No,
graph?
they use they talking about stuff that we didn't use.
Yeah. So what this person did is they turned in an old lab report, right, from like maybe last fall or last spring, or they plagiarized off of a friend of theirs who's taken this before, because they're describing the procedure that we would have done if we were in an in-class session, right? They identified the objectives, but they're the objectives of a previous version of the lab. Look at those graphs. I have one that's curving up, one that's parabolic, one that's straight down, and one that's increasing straight up. But what were the graphs that we had this semester? Well, crud. Well, if I go back to the lab this semester, right, there's objective 1, they had one like that. Here's objective 2, they had one like that. Here's objective 3. Oh, but there isn't a fourth one. So they were showing me the objectives from an old version of the lab. So make sure that when you identify the objectives, you identify the actual objectives for this lab and not someone else. The lab report that I'm looking at there, that's not a lab report that was done this semester. That's going to get a 0 because that's a violation of the plagiarism rules. That's a really big deal, and that can get you into like disciplinary trouble. So please don't do that. So identifying the objectives. Make sure you tell me precisely what the objectives are, because I should be able to know the objectives just from reading your lab report. That might include including screenshots or captions or caption figures. Or at least verbal descriptions. Where appropriate. Right. So that's definitely something that you guys want to make sure. I shouldn't have to guess what the goal is. Let's see, did I have a good one? Thought I had a good example of a background section where they do at least that part pretty well. And unfortunately, I didn't write down in my note which ones that was. I think it might have been. Nope. Thought that one was solid. Maybe this one. Yeah, here we go. Here we go. This is one. do a portion of the screen. So here's a background where they do a pretty good job of, setting up what is the goal, right? Now, part of this is a little extraneous. So they basically here they've given me a very brief introduction of what kinematics is. That's going to be important because they have to explain the physics, so that goes towards doing that. But then they waste very little time saying, we have 5 objectives in this lab. We want to generate a position graph that looks like this. Boom, there's the position graph. One that looks like this, one that looks like this, and then the 2 ones that were verbal, they tell me what those objectives were. So at least in terms of identifying their objectives, this student did pretty great. However, there's a couple of things they could have done better. What were those things? So you'll notice I don't see a single equation anywhere in that background section. Nor do I have any explanation of what the shapes of the graphs have to do with the position or the velocity or the acceleration. A person who doesn't know any of this stuff is going to look at that information and they're not going to know what to do about it. They're not going to know, how am I going to make this work? So you've got to give them that background. You have to give them that information. So at this point, we have to include another item in my list of things to do. Explain enough physics to get context. Now, I don't expect you to write the entire first chapter of the textbook and explain everything there is about kinematics. But I do expect that you're going to have to talk about the features of kinematics that are most important for understanding what's going on in the lab. So in that first lab, we were dealing with specifically those graphs. So what do those graphs have to do with position, velocity, and acceleration? Well, in that context, for example, we know that the velocity graph is the slope of the position graph, right? If you don't tell the reader that, they're not going to know. And why is that important? Well, it's because when you see an objective where you're making a position graph that curves upward, well, that's a position graph where the slope is getting steadily larger over time, which means your velocity has to get bigger. And since your velocity has to get bigger, that's going to imply that your acceleration had to be positive. Right? You need to explain that to the reader so that they realize, aha, when they go to make that graph, the curvature of that graph tells them something about the acceleration and the velocity. Right? If you don't make that case, they're not going to know what's going on when they get to your procedure section. So that's something you're going to have to do. All right, let's take another kind of a common issue that I see. And hang on, let me set the share up before I do it so I don't put somebody on blast. Let's go back to, this one. So I'm going to share a portion of the screen. So here you can see that this student has done what I've suggested by talking about the curvature of the graph and how the shape of the graph is related to the kinematics. So when it comes to getting the points for explaining the physics, they're going to be earning those points right down here. Because they're explaining to me, if the line is curved upward, then the acceleration is positive. But if it's curved downward, the acceleration is negative. A straight line suggests a zero acceleration, right? So the slope of that position graph is the velocity. So they're telling me what I need to know about the physics and getting those points in that paragraph. However, they're also doing something else that is perhaps less effective. And that has to do with the nature of equations. 10 points out of 20 in your background section come from your equations. And what you're asked to do is to derive the equations that are useful in the lab. However, what this student has done, and it's a thing that I see a lot of students do, is they just kind of went up and said, oh, here's some equations. Boom, there they are. There's all the kinematic equations. But the question is why? Why are they telling me those equations? And why are they telling me those equations right now? That's a little bit less clear. So the next big sort of to-do on my to-do list has to do with when you use equations and when you don't. And I think the general rule of thumb ought to be that you want to use equations to make a point. The equations should be in service to whatever the point of your paper, not just to include them. So what that student had just done was they just listed all of the kinematic equations of motion and said, oh, here they are. But what should they have done instead? How could they have made use of those equations in a better way? Well, in terms of the equations that you might have needed to cite in that first lab, you might have had to cite the definition of velocity or acceleration. So I wouldn't fault you for explaining, as a part of explaining what velocity is, if you had included, something like that as an insert somewhere in your paper. Or when you talk about acceleration, you say, oh, acceleration is the change in velocity over time. That, of course, is equal to this. So seeing equations like this just as part of your explanation, that makes perfect sense. I certainly would have included those. The other reason that you might need to include those 4 kinematic equations is because in the lab, we had some specific objectives, blah. And I'm failing at screen shares. Portion of screen. So for those, we had these objectives 4 and 5. You had to be able to accomplish those goals, right? And in order to accomplish those goals, you probably had to do a little bit of math in order to make them work. So where the equations would have shown up in your background section is in your explanation of how you were going to make those things work. So for instance, what would that have looked like? Well, in objective 4, the man you had to begin to move at the house and travel toward the tree, turning around just as he reaches the tree. And what typically people did was they picked a value for his starting velocity, but then they had to figure out what acceleration would make him turn around at the right moment. So you had to solve for the acceleration. And so in your paper, you're probably going to tell me that that's what you're doing. And so what I might have expected to see in that paper was for you to say, aha, in order to make him turn around at the proper moment, we had to use the time-independent velocity equation, or what Dr. Fleming refers to as the velocity or the stopping distance equation, and it relates several of your kinematic variables together, and it looks like this. Boom. So you write this out. However, in our scenario, we were solving for the acceleration, and we were able to freely choose, or the scenario chose for us, each of the other variables. So algebraically rearranging this expression, we ended up with something like that. So where would you have included equations? I probably would have included those. Why is that important? Because in your data file, you're going to have cells, and one of those cells for objective 4 probably had an A in it, and this equation got used in your data file. And so what you're doing in the background section is you're explaining to me where the heck this came from. Why is this in my data file, right? Otherwise, the person reading your report, when they're looking at your data file, they're going to see a cell with an acceleration in it and some weird formula that they don't recognize. They're not going to know why you did that. You've got to explain it to them. So you use the equation to help make it clear where you picked that acceleration from. You're using that equation in order to help you make your point, not just to list them. I probably wouldn't have even included the other 3 equations of motion for this particular lab report because you didn't actually end up needing any of those equations of motion. So make sure that when you're using equations in your equation, in your background section, that you're including the ones that make sense to include, but you're not wasting your time and mine by including extra ones. So that's a pretty big item on the list, and a lot of you could probably do a better job of using equations in a way that serves your point. Got another one that I want to address, and again, I'm going to pull a portion of the screenshot that does hopefully not include anybody's name. And which one did I need? I needed this one. Whoa. All right. Oh, shoot. All right. Sorry about that. Didn't mean to out you. All right. What's wrong with this lab report? What are they doing that they probably should not have done? What are they going to probably be fixing right after this class?
The paragraph.
They did what?
It was okay.
No,
I'll give you a hint.
Oh, second person.
Yeah. This person's lab report is riddled with second person narrative. And that's one of those 7 deadly sins that you need to avoid at all costs, right? So if this is you, fix it. Turn it back in. I'll grade the fixed version rather than give you the 0 for this one. Make sure you avoid using the second person narrative. How should they have phrased this particular stuff? What should they have said instead of saying you all over the place?
I or we.
Okay. So if I'm rewriting that first sentence, what would I have done? How would I rephrase that first sentence to not use the word you?
In physics, we learned about the components of mechanics, which is the study of motion.
You could. Now, me, I'd personally probably punch that up even more, because at this point, remember, I'm trying to avoid extra flowery bits. And what I might simply say is, mechanics is the study of motion, right? It has two pillars, the first of which is kinematics. That's the ability to describe an object that's in motion. In kinematics, several terms such as position, displacement, velocity, acceleration are used to describe the motion of an object, right? So I'm rephrasing things away from the sort of the broad and flowery, and I'm kind of being a bit more direct. Yeah. But yeah, definitely make sure you avoid second person narrative. Notice, by the way, in the procedure section, you've got the same problem. Even though the word you does not actually appear anywhere in their procedure section, if you look at like this right here, proceed to solve objectives 1 through 5. Well, one, that's super, super general because you're not telling me how you would solve it. But more importantly, you're giving somebody else instructions. But if you're giving someone instructions, that's called the imperative case. And the implied subject of that sentence is the person you're addressing. But you're not giving someone instructions. You're telling someone what you did. So what I would probably do if I was rewriting this is, first of all, I would completely just eliminate that entire first step, right? That's not really telling me anything of use. Then what I would suggest is, like, when you say, set your adjustment for each variable given, be specific. For objective 1, you had to make certain choices for those variables. What were those choices? So in your procedure section, you need to be as specific as you can be. Don't gloss over stuff. Don't generalize, because this is where you want to sort of zoom in on the specifics of what's happening. So I'm going to move that down. And I had an example of somebody who did that pretty well. And that was this person. Oops. All right, there we go. Making sure I don't get that person's name. All right, their background section has some of the same problems some of the others do. I'm gonna check the wording on this. This might be plagiarized. I might have to bounce them for that. But here they're doing a pretty decent job of explaining very specifically what they're doing. So in objective 1, the graph began at x equals 0. And that suggests the moving man had to start at position 0. So when they're choosing what to put in that simulation, they've explained in that first step that we're making the position be 0, right? Using the graph, we determine the velocity and acceleration would be positive. Now, they probably should have justified that a little bit more specifically. What is it that says that it's positive? It's the slopes. That first graph was going up and to the right. That means it has a, in general, positive slope, so the velocity had to be positive. And it was curvy and bending upward. That suggested that the acceleration had to be positive as well. So they opted to start the position and the velocity at 0. They chose their acceleration to be 2, and yada, 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 they got their graph. So they're being very specific about what choices they made and why. Objective 2, the line was straight, indicating it is negative. They probably should have been specific and said indicating the velocity is negative, because otherwise it's unclear. But at least they're telling me, here is how the shape of the graph is informing the choices that we make. And that's the sort of thinking and the sort of procedure section that I'd like you guys to utilize. Make sure that when you make a choice, you're explaining to me why you make that choice, and you're being as specific as you possibly can be. They're going point by point by point through each objective, rather than generalizing and saying, oh, solve all the objectives. That's too broad and not especially great. So in terms of procedure sections, that's a pretty important element. All right. There was one more that I wanted to call out, I thought. No, I guess not. Is there one on the back, perhaps? Nope. All right. I had to check my notes. The last big thing that I want to address is what happens in your results section, because some of your results sections could use a little bit of work. Now, it's hard to say because part of what's happening is your first lab was super quantitative or qualitative, so your results section is going to look a little different than it will for a more quantitative lab where you're doing a lot of number crunching. But in your results section, you got to tell me what your result is. And several of you guys had a results section where you didn't tell me what the answer was. Like nowhere in that results section does your graph appear. So I guess if I was going to do another bullet point, five, your results section should include your results. All right. And be specific. Now, what's going to happen is in the background section, you always gave me an objective. You had a certain question you were trying to answer or a thing that you were trying to do. So in the results section, you have to show me that you got the answer or that you did the thing you wanted to do. So this week, our objectives were, for 1 through 3, make some graphs. And then for 4 and 5, it was make the guy do a certain thing. Go from here to here, turn around, or whatever. So in your results section, you want to verify that these things all happened. So in your results section, I should probably include the 3 graphs. And for sections 4 and 5, you should at least say, we chose these parameters and he did the thing. And hopefully it did. If you could demonstrate that it did, that would be super awesome. But without embedding a video, that's probably difficult. But you could at least describe visually what's happening and what parameters you chose to make it happen. But that's not the only things you get points for the results section. In a results section, there are 4 things I'm looking for. One is that you give me the results. That's like 5 points out of 20. The next 5 points out of 20 is you compare as appropriate your results to the expected result. So for instance, if I was trying to do an experiment where the object was to measure the acceleration of gravity, I expect to get an answer of 9.8. That's what we think the acceleration of gravity is. But for any number of experimental reasons, when I do that actual experiment, I may get a value other than 9.8. There's limitations in our ability to measure things precisely. It turns out that the acceleration of gravity varies slightly at different locations on Earth. There are, sometimes bits of systematic error where maybe your measurements are all off by a reliable amount that you can't account for. Maybe there are elements that you'd like to include in your calculations, but you can't, so you had to approximate them by pretending like air resistance doesn't exist when it really does. But whatever those things are, you may get a value other than 9.8. Maybe you got an acceleration of gravity of 9.6. Well, you want to make sure you compare your value to the real value. In an experiment like that, the easiest way to do that would be to calculate what % error that was. But in a more qualitative laboratory like we had this week, the comparison would have to be a bit more broad. So for instance, if you're looking at your results, your objective 1 parabola might have bent up more gradually or more quickly than the one that you were trying to emulate. So you could at least talk about how it's different or what those differences come from. And again, I'm looking for something fairly qualitative from that section rather than quantitative. I'm not expecting you to crunch any numbers, but you should at least address the degree to which those two elements match. And if there are differences, you should point them out. I want you to get good about making those sorts of observations and addressing them, because that's part of what being a good scientist is. Now, there's two other elements in every results section that tend to get ignored by a lot of students. Those are specifically, if I go to the lab report style guide, so if you go into the lab report style guide and you scroll down to the procedure section, 20 points are going to come from, did you assess the precision of each instrument that is used? And potential sources of experimental error are identified and assessed. And sometimes it's hard to wrap your head around what that means. So let's talk about how I would assess the precision of each instrument in a lab. Well, in the Moving Man lab, what was the instrument? What measurements was I actually taking? Well, we were going to this simulation. I'm waiting for a year for it to boot up. Sadness, no more drink. So, when we talk about the precision of an instrument, how precisely can we measure stuff? Well, let me just pop over here, give this guy a velocity. And you'll notice it's measuring its position. But look at that number. Right now it's 3.542. So it knows the position of this man to the 1/1000th place. So you were measuring the position of the man with an instrument that could go down to the 1000th place. So the precision of my position measurements is going to be dictated by that display. I can't measure where he is to the 10,000th place or the 100,000th place because it doesn't have that many decimal places. But I can say the precision for the position in this case was known to plus or minus 0.001. That's called the least count of the device. Now, what about the other things? Well, if I could I go all the way down to a tiny little acceleration like that? Nope. Turns out when I made the acceleration be 0.00001, it basically couldn't tell because it was so tiny, that was too small. But if I reset everything and I make my acceleration be 0.001, you'll notice that I can get similar levels of precision from each of the other instruments. So what that tells me is that the uncertainty in all three of my devices is similar in range. The computer can only measure his position to 0.001 meters, his velocity to plus or minus 0.001 meters per second, and the acceleration to plus or minus 0.001 meters per second squared. And that has implications. If you were doing your math for objectives 4 and 5, and you calculated your answer, you wouldn't want to carry it out to more precision than your instruments themselves. So if I look back at the lab reports, and again, I'm going to share a screen portion. Let's look at this one. Yeah, so I don't know if you can see this, but down here, they've done some math to calculate their velocities. But look at all those decimals. Those decimals are going way, way further out than the actual precision of the instruments that they were using. So they probably should have truncated each of those numbers. So what's going to happen is this person is going to lose points because they're keeping their sig figs either too few in these cases or too many in these cases. So you're going to need to make sure that you think about the precision of your instruments and what that implies for your results. In this case here, 0.001, that's pretty precise. It means that most of your values are probably going to end up having about 4 sig figs at any given time, which is great. So imprecision is not going to play a big role in this result. And in fact, you'll find that when you went to make that parabolic curve, it's going to look nice and sweet and perfect and parabolic. Because it's a virtual lab with a high degree of precision, you don't expect large sources of error. But you got to tell me that, right? You have to assess that source of error. And you'll find that sources of error are going to end up being small on virtual labs like we're doing this semester, but you still have to call it out. Right. So do make sure you do that. So in terms of, I guess, broad, big picture stuff from each of the sections, those are things that I've seen that I definitely want you to do better for. The other thing that I will point out from the lab style guide is that you're getting 20 of your points for general style and readability. And one of the ones that I want to pay a little attention to is this point right here. This 10 points for the report has a clear narrative and it tells a complete story of the experiment. And of course, I guess it's kind of a related element. The part after that is that you're putting the information in a logical, well-organized sequence for all sections. And that's a place where some of you guys could maybe use some improvement as well. And that's probably the hardest part, really, is getting those two things down, particularly when you're still just getting your feet wet with physics, because you don't feel comfortable enough in the background material to be able to write confidently. So if you're falling a little short there, don't feel too bad yet. That's kind of what I expect. That's where I expect most of the room for improvement to happen, is like right in that last 15 points. But here's kind of what I mean by these two things. When you go to explain something, the order in which you present information often is important to choose. So if I'm teaching a new topic, a lot of times what will happen is I'll give you the big picture before I drill down to specific examples, because I don't want you guys to get so bogged down in the minutia of the specific examples that you miss the big picture. But let's try something even more relatable. I play a lot of board games because I'm a huge nerd. And sometimes what happens is I've got a bunch of friends coming over and I have to teach them how to play a board game that they've never played before. And when you're describing how to play a board game, you're telling that person a story. And you want to tell it in a story where it's easy to follow along with what's happening at every step of the way. So imagine that I was, for some reason, going to have my friends over and play Monopoly, right? I'm choosing Monopoly because it's a game that virtually everyone in the universe has played, which is sad because it's also one of the most terrible games ever made. I would never have my friends over and play Monopoly because I hate it. But if I was going to do it, if I had an aneurysm or a stroke or something and somehow decided I wanted to play Monopoly, what I would do is I'd bring my friends over, and assuming they had never seen Monopoly before in their lives, I'd have to explain it to them. So the first thing I'm going to do is I'm going to give them the big picture, right? The goal of this game, the object of the game is to earn money and cause your other players to lose all of their money, right? That's how you win, right? I'm going to tell them that up front. I'm not going to make the first thing I tell them, here's what happens when you roll the dice, or here's what happens when you buy properties. All of those rules are important, but the big picture is you're going to start off with a certain amount of money, you're going to buy stuff and charge people for using your stuff, and the goal is to make them run out of money before you do. That's the goal. And so everything they hear from there on out is going to be interpreted by the person listening to you in regards to that overall goal, right? Then when I'm choosing what's going to happen next, I'll pick something else. Maybe I want to talk about, how much money do you have? So every player is going to start off with $1,500 broken down into certain denominations, right? When they make one complete trip around the board, they'll earn $200 more, right? So now they have a sense of where the money starts at, where it's going to come from. Then maybe I'm going to talk about how they roll dice and move around. Then I'm going to explain how they purchase properties. And then I might explain how the rent for the properties depends on things. But I'll start with the general, and then I'll drill down the specifics. I'm going to talk about what happens when you buy a property first. Then I'll talk about what happens when you buy hotels, right? I don't want to start with the hotels and then talk about buying properties because that's in a weird order. And something similar is going to happen in these lab reports. There's a reason we start off with that background section. That background section is where you're telling them, this is what I'm trying to do. This is my goal. And this is the stuff you have to understand to get to that goal, right? Then when you get to the procedure section, that's where you're drilling down and you're giving them more details. In my Monopoly example, the procedure section would be the place where you talk about, how do you buy new hotels and houses for your properties you own? What are the rules about that? What are the rules about auctioning properties or the rules about mortgaging properties? Those are things that are going to be buried down after I've already explained the big picture of you're moving around and when you land on stuff, you can buy it. I would start with that. And then I would drill down on the more specific stuff about like, well, what happens if you land on a property and you don't want to buy it, you have to auction it off, which is a rule that nobody ever uses, but it's in the rule book, read it. I would do that later. So start with the broad general. Once you kind of have a sense of where everything fits, then fill in the details. The other thing is that you want to make sure that each point you make follows logically from the ones before it. So a lot of times what I see students do is, they'll get to their results section and they have no idea what to write. But the idea is, in your results section, you're going to tell me, hey, here's the answer to the question that I got. Now, I can trust that answer to a certain extent, limited by the precision of my instruments. Those instruments have a precision of blah, 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 and that has the following implications for the results that I just cited to you. So that results section tells a story, and during that story, I'm earning the points for telling me the answer, comparing it to the regular value, commenting on the precision, and evaluating sources of error. Those four things, they're interrelated, and you're not just sort of shooting one out, shooting the other out, shooting the third out. There's a flow, and you're transitioning from one thing to the other. Make sure that you point that out when you're writing your results section or your procedure section. And you're telling me what you did, you also have to be telling me why you did what you did. That's actually one of where is it? Yeah. One of your objectives is to explain why you did what you did and not just what you did. And so it makes sense as you're telling me what you did to also be explaining why, right? That's going to be integrated into the flow of the information. You know, you're not going to explain, you know, why you do something in the first paragraph and then 3 paragraphs later tell me what you actually did. You put the information together because it makes more sense logically for you to say, hey, I'm doing this because of this. So make sure that you're thinking about how you present your information so that you're giving the information that your reader needs at the moment at which they need it. Are there any questions about sort of what all this is? Do you guys have a sense of how you can make your lab reports better? Yes, no, maybe. You don't know.
Yes.
Let me switch gears real quick. And again, this is where we're a little bit limited by the fact that I haven't seen a lot of them. But that projectile motion lab report is a bit more quantitative than the first one. And if I can, let me look at that one submission. Let's talk a little bit about results in that context so that it's not all just this one lab. Portion of screen. All right, so here is from the one student who submitted their results section. So what they did, they results, and then boom, here's a screenshot, right? Because what was the first objective in that lab? It was to simply have, you know, 3 shots all on the same screen, 2 of them that land in the same place, 1 of them hits the guy in the swim trunks, and that was it. Now, what they probably should have done is compared that to what they expected to get a little bit better. They didn't give me any commentary. So they probably should have commented more and talked about how, like, oh, these guys didn't land exactly in the same position. Why is that? They should have. They also had a find the relationship between the, what was this one? The mass. Yeah, they probably should have labeled that chart. Because if I can't tell what it is, I get confused. But yeah, here they're making the mass larger and the distance gradually becomes larger. This graph does not have much precision because it does not line up well with the trend line. So at least they're commenting a little bit. They might have speculated a bit more about what this means. One thing that you would find is that if you turn the air resistance off, what would have happened was it would have always gone the same distance, and it would have been the distance that this is gradually creeping up towards. So the conclusion that you might draw from that is that as the mass gets larger, the air resistance starts to matter less and less and less, until by the end, it's barely any different from the answer without air resistance. And it's only when the mass is super tiny that it starts to make a drastically big difference. And looking at this expression, you could guess like what the function might be. And this looks like some kind of 1 minus e to the negative m over something kind of equation. Now, do I expect you guys to be able to guess something like that? Probably not. You don't have enough experience to be able to make that guess, but we're going to see something very similar next semester where we will make that guess about a relationship. But at least commenting conceptually that, you know, we're getting closer and closer to the non-air resistance value the higher the mass gets. That's probably a thing that student should have commented on in order to get the full set of credit. You know, when they go over here, oh, this is kind of lightly curved or maybe even linear. Over here, they're looking at this and like, oh, this looks like a parabola. See, that's great because they took their result and now they're drawing some conclusions from it. And it turns out they're exactly correct. This is a parabola. And from theory, we expect it to be a parabola because the non-air resistance version of that same thing would have been the range equation that we learned in class. And in fact, all this stuff is a constant. This is my variable. And yeah, if I do y versus x squared, it's going to be a parabola. So by making that comment, they're showing me that they're not just cutting and pasting some graph they don't know what it means, but they're thinking about what it means. And that's excellent. That's what I want to see. So make sure that you don't just throw me information without context. You also have to give it context. That's where that 15 points where you're telling me the story, that's where those 15 points are going to come from. All right, so I've yacked at you for longer than I wanted to, but hopefully that's going to help you guys write lab reports that are a little bit better. If you found that something we talked about today was something you didn't do as well as you probably should have, take the opportunity and within the next day or so, just go back and re-upload a new draft of those old lab reports, and I'll grade that draft instead. And if you turn the original grade lab in on time, I won't even apply a late penalty for your return submission because you obviously did it okay the first time, but I'd like you to revise it a little bit. And hopefully, by the time you get through this whole process of writing all these stupid lab reports, you're going to be way better about expressing yourself in a technical context. All right, any other questions before I hit this button?
Yeah, I got a couple.
Okay, what's you got?
For objective 2A, that's the mass against the air resistance or versus the air resistance. We're not changing the velocity, right? We're just changing the mass.
Yeah, like in an experiment, when you design an experiment, you always have what you call your independent variable. That's the thing that you're changing. And then the dependent variable that should change depending on what you choose. But you never want to have any other variables besides those two things. You don't want to change two things at once because then you can't be sure whether the resulting dependent variable you get happened because of the first thing you changed or because of the second thing you changed.
Okay.
It's like if you were testing a drug and I think this drug makes headaches go away, and I wanted to design an experiment to see whether or not that drug worked. Well, what would I do? I'd get a bunch of people with headaches, right?
Mm-hmm.
And I'd give the drug to some of those people, and I'd probably have a control group that I didn't give the drug to, and I'd be like, okay, so the people without the drug, their headache went away in 3 hours, but the people who took my drug, their headache went away in how much time? And if they went away in less time, yay, my drug might work. Make sense?
Mm-hmm.
But what I wouldn't want to have is if those two groups, the only difference between those two groups is did they take the drug or did they not take the drug? What I wouldn't want to do is to have the people who took the drug, maybe they're all women, and the people who didn't take the drug be all men. Because now I got to wonder, maybe there's a hormonal issue, right? Maybe estrogen inhibits my drug activity, and I don't expect it to work as well on women as men, right? I don't know. So if the two groups have their headaches go away in a different amount of time, I can't be sure if it's because they took my drug or because they've got a different set of hormones, right? Mm-hmm. So instead what I would do is when I pick those two groups, I'd either pick all men or all women for both groups, or I'd make sure the mix of people is sufficiently similar between the two groups that the difference in what happens to the two groups shouldn't be attributable to it.
Okay.
So only ever change one thing at a time. And even in physics, that's true. So if you're making the mass larger and larger and larger, leave everything else the same.
The same. Okay. Yeah. And for 2B, what are you looking for exactly? It says diameter versus air resistance.
Same thing. Right there, you're going to leave the mass the same every time. You're going to leave the velocity and everything else the same. But what you're going to be doing is you're going to be cranking up the size. So at first, I'm shooting little tiny cannonballs. Then I'm shooting bigger cannonballs. Then I'm shooting bigger cannonballs.
Okay.
Right? And the idea is if the size of the cannonball matters, then I should see a different result for the big cannonballs than I do for the smaller ones. And in fact, we now know enough. We didn't know this last Friday, but we know it now. We know that the area should matter. How come?
I don't remember.
Well, because what's the formula for air resistance? Don't remember. So for air resistance, the viscous drag was 1/2 CA rho V squared. And so what's going to happen is when you're making that cannonball bigger and bigger and bigger, you're making A get bigger and bigger and bigger. So those small cannonballs, they're going to feel some air resistance, but it's not going to be nearly as much air resistance as those big ones. So I expect the larger I make the diameter, the bigger I'm going to get the drag force to be. And it's going to therefore cause it to deviate more and more and more from the non-air resistance answer. And in fact, the student who I screen shared earlier didn't observe this, but they could have. Let me go back to that portion of the screen thing. So here was their result for objective 2B. And if they had done like that same shot with no air resistance, what would have happened was it would have been like this. And I would have gotten the same result for everything if there'd been no air resistance. But what's happening as the diameter gets bigger, the air resistance matters more, and it's getting further and further and further from the non-air resistance answer. So for the sufficiently tiny ones, you barely even notice. But for the sufficiently big ones, there's a big gap between those two lines.
Okay, I got a better understanding.
All right. Oh, and I said one more thing that I would do today when Abigail asked about it, and that was the quizzes. So let's go ahead and talk about those conceptual quizzes and see if we can't make sense of some of those. I don't want to full on answer them. How am I going to do this? How am I going to do this? Because they're still open. People are still taking them. So, how do I do this and still be fair? So let's pull this up real quick. So here's that first kinematics quiz, right? And the first one, I want to figure out which of those things can potentially be negative. Well, vectors keep track of their direction with pluses and minuses. And so you want to ask yourself, which of those things are vectors and which ones are not? For this one here, this one is pretty straightforward. You're looking for velocity. You have to know the definition of velocity. So the definition of velocity is how far I went divided by how long it took. Super easy. For this one here, you're thinking about an object you throw straight up into the air. It's going to go up to some maximum height, fall back to its neutral position. And you want to think about which of the statements is true. Well, you know that once it leaves that person's hand, it's being affected by gravity. And gravity has an acceleration that stays the same the entire time. So that should be enough to answer that question. Question 4 is tricky. Obviously, the only surefire correct answer is that Superman is the best superhero. And anyone who picks that as the incorrect statement is dead to me. And I don't even know what to do with you guys. But this is tricky. And the reason that it's tricky is because sometimes students, they don't have an easy understanding of how velocity and acceleration are connected to each other, or what acceleration really means. So remember, velocity is the rate of change of your position. It has a magnitude and a direction. So I could be traveling 5 meters per second to the right and call that positive, or I could be traveling 5 meters per second to the left and call that negative, right? Now, acceleration is also a vector. But what's going to happen is if my velocity is positive and my acceleration is also positive, I'll be slowing down. If my velocity is negative and my acceleration is also negative, I'll be speeding up. And so what's going to happen is acceleration doesn't tell you what direction you're going. It tells you how is your velocity now going to be different from your velocity 1 second from now. If your velocity is going to be a larger number, then your velocity is going to be, or your acceleration is going to be positive. If your velocity is going to be a lower number, then your acceleration is going to be negative. So going from a velocity of +5 to +10 would be an acceleration that is positive because my velocity went up. Going from a velocity of +5 to 0 would be negative. Going from a velocity of -5 to -10, the acceleration would be negative because -10 is the lower number than -5. And so hopefully that should sort of clear some of that stuff up. And for each of these, you're thinking about it in terms of, definitional prospects. Yeah, actually, I think I'm going to maybe not comment on those on a broadcast. If you've got questions about a quiz, make an office hour appointment for me, and I should probably address the rest of them there. Because again, some people still haven't taken those quizzes. The quizzes are still open, so I can't just say the answer is this because then it sucks if you answered it before you talked to me and somebody else answered it after. So I don't want to do that. But I also want you to have a bit more armament going into the exam. I don't want you to not know the answers to these things before you go to the exam. So if you've got questions about those, hit me up and we'll address them. But I don't want to do it in class. The more I think about it, that's just not fair. All right. So that's it for us. Any other questions?
Nope. I think I'm good.
All right. Have a good one, folks.